you everybody for being here. Our session title is called The Reading Brain, Relations with Instruction. And we have presenter Dr. Jack Fletcher. I'm going to tell you a little bit about Mr. Fletcher. Dr. Jack M. Fletcher is a research professor, Department of Psychology, University of Houston. He has served as an associate professor from 1985 to 1989 and Cullen Distinguished Professor in 2006 all the way to 2021. He's a board certified child neuropsychologist. He has completed research on many issues related to neurodevelopmental disorders, learning disabilities, and pediatric brain injury, including definition and classification, neurobiological correlates, and intervention. The author of over 400 papers and 3 books, Dr. Fletcher directs an NICHD-funded National Learning Disability Research Center, Texas Center for Learning Disabilities, and has been funded on program projects on spina bifida and math disabilities, in addition to numerous investigator-initiated grants from NIH and NSF. He was the recipient of the Samuel T. Orton Award in 2003 and the Norman Geschwind Memorial Lecture in 2022 from the International Dyslexia Association, a co-recipient of the Albert J. Harris Award from the International Reading Association in 2006, and past president of the International Neuropsychological Society in 2009. Thank you so much, and we're so excited to have you here.
Well, thank you for inviting me.
Center is Ms. Janet Cornell, so thank you, Ms. Cornell, for
I can't hear, I'm sorry.
sacrificing part of your Saturday.
Somebody's talking or something?
Yes, give me just a second, sir.
And just to let our participants know, I will.
Okay,
Thank you.
thank you.
I was asked to give this presentation, and it's a little bit different from what I usually present to literacy audiences, which are presentations about assessment, dyslexia, bilingualism, and so on. But I'm going to talk to you about a series of studies that we've done in Houston, right down at the medical center, that involve struggling readers, many of whom are language minority students, in which we look at changes in the neural circuits that support reading in relation to reading intervention. And what that means is that in all these studies, we have imaged kids before they start the intervention, and then we've imaged kids after they start the intervention. So I'm going to talk to you about the areas of the brain that are involved in reading. I'm going to, in particular, focus on the interventions, and then show you the changes that occur when struggling readers respond to the intervention.
To see everybody.
Specifically emergent bilingual students from 5th grade all the way up to 8th grade. I did a small stint.
Sorry, I can't. Thank you. So the technical term that we use to describe the types of changes that occur in the brain when kids learn to read is neuroplasticity. It's the fact that the brain is extraordinarily malleable and changes to support certain types of skills, including reading. When kids learn to read, they're not born with the neural circuits that support reading. What happens is that kids receive some sort of instruction, and they learn to relate the sounds in language to the sounds that words make. We call this the alphabetic principle. But it's a very different process from what's involved in learning to talk or learning to walk. Those are evolutionarily based processes. We are born with predispositions in our brain to develop the circuits that are necessary for talking and walking. And all it takes is maturation and exposure to make these things happen. We can enhance it, for example, by the quality of the home language environment or by opportunities to move and exercise when you're young. But that doesn't work for reading. We can't develop the neural circuits that we need for reading simply by exposing kids to literature or reading or to environmental print. I mean, you can really understand how that happens in Houston, where we have a lot of people that are not proficient at reading. But if reading was really a natural process and only required exposure, we have enough billboards that we could replace school buses with pickup trucks. We'll put seatbelts in them and drive kids up and down I-45. And that would be sufficient for learning to read. And obviously that doesn't work because we're all exposed to environmental print. And in that sense, good reading instruction is always brain-based. It's something that teachers do every time they instruct the child. They have a direct effect on the brain, and the brain is always involved in the development of reading proficiency, and even in kids with dyslexia, which is a word-level reading problem where kids have difficulty reading and spelling words in isolation. So literally, when you learn to read, it rewrites the organization of the brain, and the extent and how that happens, the circuits that are involved vary slightly depending on the structure and the transparency of the language. And what I mean by transparency is the relation between what words look like and what words sound like. In languages like English, that is an irregular relationship. And lots of words don't look like the way they sound. But in Spanish, the relationship is much more transparent, less opaque, more direct. The same thing is true in German or Italian or languages like that. And so in English, we commonly produce kids who are really inaccurate at reading. In Spanish or German or Dutch, languages that are more transparent, they're more likely to have problems with automaticity, how fast they can read words. But it's still a breakdown at the level of the word in dyslexia and also with spelling. And the underlying neural circuits don't vary that much according to the structure of the language. So the questions that we ask is what is the relation of reading instruction and brain function, as well as structure? And when the brain changes, particularly in struggling readers, are these compensatory types of changes where areas of the brain that aren't typically involved in reading become involved in reading? For example, a simple example of that would be most people who develop reading skills read with the language hemisphere, the left hemisphere. But suppose there were compensatory processes involved and the right hemisphere became important in some people for learning to read. Or the other contrast would be normalizing. That instruction, for example, simply resulted in activation of the areas of the brain that are typically involved in reading. I'll tell you now that most of the changes that occur are normalizing. They do occur. The brain is malleable. It's malleable in development, and it's also malleable in response to instruction, even in struggling readers with dyslexia. So these are the examples of the imaging devices that we use. These pictures are from the University of Texas Medical School, where we did a lot of our research, literally recruiting kids from public schools in Houston. There are actually kids from Aldine who participated in some of the original studies around 2000 when we were doing work on language minority students in Aldine. The big machine that you see on your left that has sort of the beige cover is an MRI. It's designed to do structural imaging of the brain. The other machine where you see the little girl, she's actually almost 6 years old. is called a neuromagnometer, and it's used for functional brain imaging and something called magnetic source imaging. We can also do that with an MRI, but the principles are the same. What she's doing as she lies here is she's looking at a mirror, and that mirror reflects onto the ceiling, and there are words there for the child to read. And as she reads the words, we're able to record changes in the electrical signals that occur in the brain as she reads, and to identify the time course by which different brain areas become activated and the areas of the brain that underlie the neural circuits that have to organize in order to learn to read. So when we talk about the brain, I always have slides to talk about dyslexia because that's where most of the interest is. But in reality, the same thing happens when kids learn to read. It's not really a different process. And the key is whether the child responds to instruction or not, actually learns to read or not. There are two different systems in the brain that are involved in reading, and we have metaphors for this. There's one system that's very closely related to speech and the ability to do auditory processing of language. It's the same areas of the brain that are involved when you hear language. What you have to do is you have to transfer your natural capacity for language processing through the ears to the eyes. And learn that print represents the sound structure of language. And so that is a sublexical system, which means that it deals with parts of words, named phonemes, and it's in regions of the brain that we call dorsal. And I'll show you that. I'm teaching you vocabulary as we go. You'll see that I'm going to expose you to the word dorsal approximately 8 times in this talk, and that should be sufficient exposure for you to develop a new vocabulary word. And then we have another metaphor, because proficient readers don't break words down into their underlying phonological elements. They deal with whole words. They don't do that immediately, and it's something that you have to develop the capacity for by processing increasingly large units of words, phonemes, morphemes, and whole words, according to the statistical regularities by which letters and word patterns occur. And that is an area of the brain that is called ventral. And the metaphors are unlocking language from vision, or language at the speed of sight. And the reason we emphasize the language is that reading is inherently a language-based process that takes place in the language hemisphere. And when kids learn to read, what they do is they organize these systems that have other purposes. They repurpose the dorsal system, which is responsible for language processing, and then the ventral system, which is responsible for complex visual processing, things like maps, geography, reading MRIs, anything that's a complex visual example of visual expertise, like reading, gets reorganized into areas that are involved in the left hemisphere. So we have examples of malleability, the ability to change in development and in instructional response, but access to reading material and experience is the key for automaticity, and I'll explain what I mean. So this is based on a theory called dual route theory, which is about the two circuits in the brain, the dorsal circuit and the ventral circuit. The dorsal route is sublexical. It identifies phonological representations in words, and it's an indirect route to the meaning of the word, because you have to take a word which is usually unfamiliar, break it apart according to the sounds, and then access the meaning based on your ability to assemble the sounds into a word. So that's reading is parasitic on language, and it involves a relation of sound and print. And the brain has to learn to do this. We have to develop the systems that mediate this particular type of ability. Then we have this other route, which we call ventral. Now, keep thinking about how many times I've exposed you to this word so you can learn the vocabulary. It's a stipulated, meaning that the meaning is automatically attached to the form of the word. It's a lexical system. You go directly from the word form to the meaning, to the pronunciation, or to the meaning. And that's why we talk about reading is unlocking language for vision, or language at the speed of sight, because that is literally what happens in proficient readers. You see a word, you know immediately what it means or how to pronounce it. But you're not born with that ability, and it's something that you learn to do in development. And most of us don't remember the phase of learning to read where we had to sound out words, even if we were learning with Dick and Jane and Spot and whole word kinds of methods. You still have to access the phonological structure. Now, these systems operate in parallel, depending on the structure of the word and how much familiarity you have with the patterns that are involved in the word. So if you look here at the bottom, and you just think about what happens when you read words like the reading brain, where your eyes look at it, the visual input goes through the back of the brain, back here in the gray area, and then it goes forward so it can be processed. And visual experience goes into the bottom part of the brain, into areas that are called, the visual cortex is the occipital region. And then we go into the temporal lobes, where this interface between the temporal lobes and the occipital lobes deal with complex visual information. And if you know the word, it'll go directly through this ventral route into these areas here that deal with meaning. But if you don't know the word, you're not familiar with the patterns and so on, or you're learning to read, then it goes up into these language areas here. And up above, I've defined the regions even more specifically. In this ventral region, we're talking about an area called the fusiform gyrus, which is important for any kind of complex visual expertise. I gave you the example of map reading, for example. If you teach people to become really good at reading maps, the fusiform gyrus in the right hemisphere becomes very specialized for map readers, like in taxi drivers, for example. In the left hemisphere, if you learn to read, it becomes a very exquisite graphemic analyzer, not based on spatial relationships, like the shape of the letters or word patterns or things like that, but the statistical regularity by which words, letters, and letter patterns are organized into words. And then up here, I've shown you Wernicke's area, which is in the temporal lobes up here. This is the dorsal route. And this is an area that's very, very important for auditory processing of language. It deals with speech as a segmented signal, because what your brain does is it breaks words down according to how they sound. And it does the same thing for oral language and for print. But it has to learn to do this for print. And this part of the brain has to learn that print is an example of language, and that it's language by eye as opposed to language by ear. So this is an example of how these regions operate in two kids, one of whom is a proficient reader. These are third graders. These are actual brains engaged in a word reading task. And this is a third grader who's a proficient reader, where the yellow part is activated first. That's why it's yellow, because that represents different time courses. But we activate this area here, which is the ventral route, first. And then we get activation of these dorsal elements here up in the temporal lobe in the left hemisphere. And then if I ask you to pronounce the word, these areas in the front part of the brain called Broca's area would get much more active. Now, this is a kid who has dyslexia, and you can see that in the left hemisphere, there's no development of a neural network like the one that you see here. Instead, what you see is activation here in the right hemisphere, and in the same areas, the ventral and the dorsal regions. But this is not an effective way to read, because the brain this network is not in the left hemisphere. And so what we have to do is we have to shift. We have to help the brain shift the activation here into the left hemisphere so that we have a network that looks like the one in the proficient third grader. So a long time ago, we were working with the idea that dyslexia was sort of an immutable thing that you're born with, and that it wasn't changeable. But as we developed the capacity to really image the brain and demonstrate these differences between kids with dyslexia and kids who don't have dyslexia, we began to experiment with what we call intervention imaging studies, where we took kids that had very severe reading problems and put them in very intense interventions to see what happened in the brain, and to ask the question of whether we could get compensatory changes or normalizing kinds of changes. To be honest, when my neuroscience colleagues wanted to start this, I told them that this would not be effective, that these kids were not going to respond to the intervention, and I was wrong. We took 8 children with severe dyslexia. We put them, and there's actually a very strong research base on these types of interventions. We put them in an 8-week summer program where they got phonologically based intervention. We were just trying to teach them to decode for 2 hours a day for 8 weeks, about 80 hours total of instruction. And these kids, these are the 8 kids here. Notice that they range in age from 7 to 17 years of age. This is their word reading before we started the intervention. Some of these kids are reading at the 1st percentile, the 2nd percentile, up to the 18th percentile. This is their word reading score after 8 weeks of intense decoding activation. All of these kids are reading in the average range. That means they're reading above the 25th percentile, and their reading skills range from the word reading skills range from the 38th to the 60th percentile. All 8 kids responded. This does not work in every child, but it happened to work in this first example. It is not because these are really bright kids. A person's average IQ is 100, and we deliberately selected kids that had IQs in the average range. And it's not because they're easy to teach. 6 out of the 8 kids also had ADHD. They were taking stimulant medication. So these are restless, fidgety kids. Sometimes people wonder if we gave them the medication while they were being instructed, and the answer is absolutely, because we know that kids who have ADHD and dyslexia do better if you treat both problems. And trying to teach kids for 2 hours a day, this means 2 50-minute intervention sessions occurring one right after the other with a 10-minute break, is very difficult for kids who have trouble focusing. So of course we did, but we did not image the kids when they were on stimulants. So the medication doesn't have any effect on the brain activation patterns. So in all 8 kids, what we found were normalizing changes in the dorsal region. This is the area of the brain that's not activated before the intervention. You can see very little activation in the dorsal region here. But look at the brain after 8 weeks of intervention. There's an enormous amount of activity here, and you can even see that there's less activity here in the right hemisphere. Same thing in this child, tremendous amount of change in this dorsal region. This is true in all 8 kids. So we were pretty excited about this, and we started a series of studies to see if we could observe these types of changes in other kids. Some people wonder if the changes that we observed persisted. The answer is we followed the kids a year later without any intervention on our part, and the changes both in reading and in brain function persisted. That's a very common finding. Kids may not continue to accelerate their development, but they don't lose the changes that you see, and the brain doesn't stop functioning. It may not continue to reorganize. And a very important question is what's happening with this ventral area. Well, in order for this ventral area to change, these kids need to read a lot. Because this area is much more dependent on exposure. We have taught these kids to decode accurately. That means that they will have a significant boost in their comprehension, but they will not be automatic. And these kids were by and large not automatic in their word reading because they didn't have enough experience with print. But to develop the automaticity, you have to take your eyeballs, lay it on print over and over again in a structured, purposeful pattern to get that ventral region to really come online. Now, if you start early and you have early access to print, you will get simultaneous development of the dorsal and ventral regions. And that's what we demonstrated in this study. This is a grade 1 multi-tiered intervention study where we had an early intervention component and a brain activation component where we imaged kids at the end of kindergarten and at the end of the first grade. There were 3 types of interventions in this study. One we called enhanced classroom instruction, where we worked with the district. This took place in HISD. And we went to 6 elementary schools, and we did something we called enhanced classroom instruction, where we screened everyone. We did universal screening at the beginning of first grade, identified the bottom 20% as being at risk, and then introduced a progress monitoring system where we monitored the child's reading progress by giving them oral reading probes, 1-minute probes every month, and graphing it to see how the kids were doing. And then we worked with the district to introduce professional development and new reading materials just into the classroom. So we took the bottom 20%, and 1/3 of the kids only received enhanced classroom instruction. Then we had 2 groups of kids that received a supplemental tier 2 intervention. They got an additional 40 minutes of daily small group instruction for 30 weeks in groups of 3 to 5 kids for about 80 hours. A total of about 80 hours over the 30-week periods. They were basically getting this 4 to 5 days a week. Everybody got their 90-minute language arts block and their math instruction, but we pulled these kids out during electives and so on. And somebody's going to ask me, didn't the kids complain about that? Well, these are first graders, and there's nothing first graders like more than being taken off and be giving special time by an adult. And these kids are really motivated to become better readers. They understood the purpose of it, and they knew that reading was hard for them. So they're getting a double dose of instruction. They're getting 90 minutes of quality classroom instruction in reading and language arts, and then 2/3 of the kids are getting 40 minutes of additional instruction in groups of 3 to 4 kids. There were 2 different types of early reading interventions because we wanted to see if some types of interventions worked better with some kids than other kinds of interventions. One was a scripted direct instruction program developed by Patricia Mathis and Joseph Torgerson. It involved explicit. Now I'm going to expose you to this word about 8 times now. Explicit instruction in synthetic phonics, which is blending, with an emphasis on fluency. You learn the sounds, and then you say the sounds fast to make the words. Say it fast. But this is not a phonics program. It integrated decoding, fluency, and comprehension strategies, which were authentic stories written by hired authors and incorporated the phonics principles that we were using with a lot of practice. It used 100% decodable text with isolated practice and drills, and it was completely prescriptive. There was a manual that had a carefully constructed scope and sequence that was designed to prevent any kind of confusion on the part of the teacher. We contrasted that with the program that we called Responsive that was developed by Carolyn Denton, and that involved explicit instruction in synthetic phonics, blending, as well as word families. We had word walls and things of that sort. It taught decoding using the alphabetic principle, fluency, and comprehension strategies. These are explicit, comprehensive programs. Remember those words in the context of reading and writing. So the curriculum was organized, but there was no scope and sequence. And what teachers did is they responded to the students' needs as they were observed. And it used level text, not phonetically decodable text. You'll recognize this as an example of some of the principles that you hear in balanced literacy. But the difference is that the curriculum is very organized, and there is explicit word work with only one type of strategy, which is sounding out words, no triple cueing system. So in a typical lesson, a child would do fluency work, repeated reading, and assessment for 8 to 10 minutes. There would be 10 to 12 minutes of word work, only sounding out words, and then there would be supported reading and supported writing for 8 to 10 minutes. So common to both interventions is key instruction in areas of reading that involve phonemic awareness, phonics, fluency, and comprehension. Explicit instructions. The students were not expected to infer or construct new knowledge. It was shared directly. Systematic instruction. Thoughtful plan and purpose for selection of instructional objectives with lessons designed to teach these objectives. Intensive intervention. Students are highly engaged in a small group setting. Active engagement. They're not passive, but actively involved in reading and reading related activities. And then lots of opportunities for feedback, multiple opportunities to practice that was cumulative and purposeful. So these are the results of this 1 year study. And what I'm showing you are the progress monitoring assessments that we did every month from October to April. The group at the top are typical achievers who are not at risk. The group at the bottom are the kids who only got enhanced classroom instruction. And then in the middle, you see the two tier 2 interventions. And so the results are easy to summarize. There is no difference between these two interventions. They were both equally effective, and that's because they were explicit, comprehensive, and differentiated, the features that I showed you that they had in common. They did better than the group that got enhanced classroom instruction. But notice that the group that got enhanced classroom instruction here, that were at risk but did not get tutorial interventions, also showed a lot of growth. And all three of these groups closed the gap relative to the typical readers. The enhanced classroom instruction did not do it as well. If we look at the brain imaging studies, these are on my left, I think it's your left too. This is the left hemisphere, and then the right hemisphere is the other hemisphere. And you notice that there's not much activation in the kids doing a letter sound task if you're at risk. But if you're not at risk, notice all the activation in the dorsal region. After intervention, and also notice that we have a lot of right hemisphere activation in the at-risk kids, but not the not at-risk kids. After the intervention, we could literally discriminate kids in terms of instructional response according to the amount of activity in the dorsal region. This is a low-risk kid. Here, the left hemisphere is on your left. Look at all the activation here. In the responders, the kids who responded to the intervention, you see the emergence of the dorsal system here, still bilateral, but that's going to dissipate even more as the kids get better at reading. But in kids who didn't respond, you see no activation in these dorsal regions, no establishment of the left hemisphere network. The good news is that there were not very many kids who did not respond to this intervention. If you look at it by group, if you got only enhanced classroom instruction, there were 15 out of 92 kids who did not meet grade level benchmarks at the end of the first grade. That is 16% of that group. But remember, that is 16% of the bottom 20%. So the intervention reduced the number of kids that were at risk from 20% to 3.2% of the school population. If you got both the tier 1 and the tier 2 intervention, there were 7 kids that did not respond. That's 4% of the school population. Sorry, of these groups, and that's less than 1% of the school population. So we had about 22 kids that did not respond to the intervention. There were another 5 kids who continued to struggle, not with decoding, but with fluency. So that's 27 kids. We took these kids and we put them into a 16-week program that included an 8-week intense phonics intervention, like the one that I showed you before in the first set of slides. And then we gave them an 8-week fluency intervention to see if we could improve the automaticity that was involved. We had 2 rounds of this so that we had one group that did not get the intervention so that we could look at the effects in what we call a staggered design. But it's a 16-week intervention involving 8 weeks of intense decoding intervention for 2 hours a day over an 8-week period, and then 1 hour a day over 8 weeks of a fluency intervention. So on average, these kids made gains of 2/3 of a standard deviation. That's really a pretty significant improvement in kids who did not respond to a tier 2 intervention. But the most interesting thing is that if I graph in the red line what was represented by the average amount of change, look at the variability in the individual kids. On the right, you see that some kids did really well with this 8-week program. Some kids did okay, but they needed more than 8 to 16 weeks. In fact, they needed more time in the decoding intervention. And for some kids, it didn't work at all. They needed an entirely different kind of intervention, or we know not every kid is going to learn to read effectively. And so these kids may be persistently inadequate responders. And those are probably the kids that actually have a real bona fide reading disability based on instructional response criteria and not on discrepancy criteria, which is a static kind of approach. And then again, we image the brain. And this is the average amount of change that we saw. This is the left hemisphere here in these kids, where you see no activation in the dorsal region. And then after the 16-week program, we get significantly increased intervention in this dorsal region. Now, just so you don't think these studies are specific to Houston and the work that we've done, there are over 20 studies of intervention and imaging. I'm going to show you one by Benita Blockman that took place at Syracuse University and at Yale, where the kids received the intervention in Syracuse, but there were no MRI machines that could do functional neuroimaging. And so the kids literally flew from Syracuse to New York to participate in the imaging part of this study. We paid for it as part of the research. But it looked at the effects of an intensive reading intervention that looked at phonological and orthographic connections on the functional organization of the brain in kids who are struggling readers in grades 2 and 3 that either received a tutorial, a 1-on-1 tutorial, or whatever the school provided as standard practice. The interventions themselves were like those that I've already showed you, but it had a 5-step core that all of which was explicit, that involved the review of sound symbol associations, practice word work, making words to develop new decoding skills, a lot of sight word instruction, oral reading of stories. You're not coming on to tell me that you can't hear me, right? Am I okay? Okay. Writing of words and sentences, and then extended activities such as reading narrative and expository text to enhance fluency and comprehension, and a source of enjoyment, as like in writing activities and games. These are not drill and kill types of programs. These are the results where we have at pretest no differences between the kids. You can see at the intervention, at the end of the intervention, that kids in the treatment group improved significantly relative to kids that weren't in the treatment group, and that these gains were persisted a year after the intervention. And if I don't have this graph, in fact, the kids were followed up 10 years later, and all I would do is add 2 more data points that look like this because the results persisted for 10 years. Now, these are MRI scan results, and what I'm showing you is a composite of the areas of the brain that showed significant change after the intervention. And these are at different levels of the brain, so I can show you the dorsal and the ventral regions. The left hemisphere is the one that you see on the left, has an L at the top. And then if I just go down from the L, the yellow are changes in the dorsal regions, same thing that I was showing you before. And then further down, we have ventral area changes. So again, we're seeing normalization of brain function. And then one more quick review of an MRI study, which shows the same kinds of things, but this is older kids in grade 5 who got a year-long intervention through a study that was called Power for Kids, that compared 4 different remedial programs, about 100 hours of instruction. You didn't use a word reading task, but used a sentence reading task before and after the intervention, and then again 1 year after the intervention. And again, what we're seeing are the changes in the brain that are occurring mostly in these temporal parietal areas, comparing good and poor readers. It's the same type of change. It's normalizing of brain function in the left hemisphere that you see here in these yellow areas that I've circled. And again, we have another example of normalization of brain function. Now, when doesn't this work? Well, basically, what we know is that with any kind of reading instructional program, whether it's with typical achievers or with kids who are struggling, if the kid responds to the intervention and develops proficiency in reading, we're going to see the development of these types of brain regions. The dorsal and the ventral systems are going to become activated, and the brain is going to develop the capacity to mediate reading through these 2 neural circuits. But the critical issue is instructional response. So take an intervention where that's less effective. And frankly, any intervention that takes place in middle school and the secondary level is going to be less effective because the child is already so far behind that it's very difficult to give this ventral system enough exposure to reading material to really become proficient. It's just very difficult to do. You can get decoding changes, but the ventral changes just don't happen. So this is a study that we did in Houston, and we took kids who passed the TAKS test and kids who didn't pass the TAKS test. We did additional assessment, and we found that 4/5 of these kids had decoding and fluency problems. These are in grades 6, 7, and 8, and 1/5 had specific kinds of comprehension problems. We put them into an intervention that eventually took place over 3 years, where we took over a reading period over an elective for about 40 weeks of the school year each year. And we did this for a full year. And in the first year, on a reading comprehension measure, we got no differences. The year of intervention basically had no effect on reading comprehension, but in the first year, virtually everybody was getting something from the school. They either got our intervention or nothing from the school. This is not true in the second and third year. And what you can see is that by giving the kids 2 years of intervention, the slope is accelerated, and the differences between kids who aren't getting the intervention is larger, And by 3 years, the difference is really quite large, but that's because the kids that are not getting reading support are actually showing decreased standard scores. Now, if I showed you the raw scores, you would see growth in reading in these kids, but they're not keeping up with the typical achievers or with the kids that are in treatment. Now, why is that? Well, what we found is that kids who did not respond to this intervention using fluency criteria showed underactivation, particularly in these dorsal regions, because so many of them were poor decoders, and we found that activation of the dorsal reading predicted response to intervention. So these are the kids before the intervention, and you can begin to understand why some kids respond and some kids don't respond. At the top, we see typical achievers who have the left hemisphere is marked by LH, but they have enormous amounts of activity here in the dorsal regions. Kids who responded to the intervention, these are typical achievers at the top. Then kids who responded to the intervention have some activity. They're prepared to learn to read. They're not as severe. But then kids who did not respond showed very little activity in these dorsal regions. They just did not have enough going on in their brain to really respond. This is not brain structure. This is brain function. These brains are visibly normal. But if you wait, it becomes increasingly difficult to get the brain to respond, not because of age, but because of reading experience. And here, what we've done is we've mapped the changes to changes in the brain that occur in the structure of the brain. And what's happening, you can see on the left hemisphere here, is that we're getting significant changes in the ventral area. This is a measure called cortical thickness, which is the thickness of the cortical mantle, that there's actually increased cortical thickness in relation to learning to read in these struggling readers. That's what these yellow areas mean in both the dorsal and the ventral regions. So I'm going to wrap up. When we talk about struggling readers, is plasticity an issue? Most likely for some readers, but the only way to know who they are is to provide them with instruction and see how they respond. People get upset when I say things like, you can't really know who is dyslexic until the child has had a clear opportunity in an intervention to learn how to read. So I tell people not to diagnose dyslexia unless you can document that the child has failed to respond to a really intense intervention. And that's because the neural systems that underlie reading seem malleable. They show plasticity across the age range, and they're not disorder specific. It's a continuum where dyslexia and kids who struggle to learn to read are the lower end of a continuum of severity. The changes are mostly normalizing, not compensatory. We don't know nearly enough about inadequate responders yet, and that's the focus of the research that we're doing. We need to do more work to tie functional results to structural correlates. But what's interesting is that these kinds of changes parallel the differences that you see in literate and illiterate adults who learn to read. And we do know that neuroimaging measures are effective predictors of growth and intervention response, but we don't need to do neuroimaging with every kid. In the future, we have developed portable imaging devices so that kids do not need to come to the Texas Medical Center to be imaged. If our recently proposed research is funded, we will be able to set up portable, non-invasive, none of this is invasive. We're not doing anything other than recording magnetic signals that come off the brain when kids engage in cognitive tasks, or measuring changes in blood flow non-invasively, just using sensors that detect it. But we now have the capacity to do this using portable devices that we can literally bring to the school and image kids as they participate in learning activities. And we plan to do this not only in response to intervention, but to try and learn more about the neural processes that occur as students interact with teachers. And we look at things like synchronization of learning in engagement, not just what happens in the brain before and after an intervention, but what happens during a lesson. What kinds of brain changes occur, and do these help explain why some kids learn to read and why some kids don't? So we're very excited about that, and we really hope to be able to use these kind of portable devices starting next year if our proposed research is actually funded. So I'll leave you with this thought. Reading sculpts the brain, but it has to be taught. Who does the instruction? Who changes the brain? It's not me, it's the teacher. Teachers do this every day. Teachers are neurosurgeons. They change the brain. Alvin Lieberman said that we are all born with dyslexia, meaning that none of us are born being able to read. The difference among us is that some are easy to cure and some are not, which means that some kids respond really easily to instruction, but some kids require a lot of effort. If you have questions, I'm going to take questions. I don't know if we can do that or not, but I'll try. You can email me at my email, which is here, and I'd be glad to respond. There'll be copies of the slides on our website here, www.texasldcenter.org. I'll post them next week, and we're supported by the National Institutes of Health. Thanks very much for your time.
Thank you, everybody, for attending, and thank you, Dr. Fletcher, for all of your amazing information. We really appreciate you here being with us this morning. So I just linked the attendance form, and remember, our next session will start at 1 o'clock. Okay?
Thank you very much. Have a nice day.
Thank you.